All right, guys and gals, we're going to wrap up chapter 6 today by looking at section 5. We're going to look at parts of similar triangles. So what we mean by that is we've been dealing with similar triangles. So let's draw one out here real quick. That's a horrible drawing, but we'll go with it. So far, we've been dealing with things like angles. We've been dealing with things like sides. Today, we're going to deal with special parts. For example, things like an altitude. So let's draw one in for each of these. So our altitudes, as it turns out, also are proportional the same as the sides. For example, if I mark all my angles that are congruent, there they are. Notice that the triangles that are formed with the altitudes also have to be similar. They have an angle here, they have an angle here, so these two triangles on the left are similar. Notice these sides are proportional because they're part of the overall triangle. Because these smaller triangles are also proportional, that means their altitudes are also proportional to the entire triangle. So that's the kind of stuff we're going to look at today, is similar parts of similar triangles, but in this case, the special parts, things like altitudes, things like medians, they also hold that same proportionality. So that's what we're going to investigate today. Take a look. Let's start with perimeter first. As it turns out, perimeters of similar triangles are also similar. In other words, they're proportional. So the proportional perimeters theorem states just that. If two triangles are similar, then their perimeters are proportional to the measures of corresponding sides. So take a look. In this particular case, I know that my two triangles are similar, QRS and then LMN. I know the perimeter in this case of QRS. We can add up those sides very quickly and see that we get 84 units, whatever we're measuring in. In order to find the perimeter here, we've got a couple options. One option is to keep setting up proportions for each side using this first one, 5 and 12, find the other two sides, and then add them together. That works. A quicker solution would be, for example, I've got 5 on the smaller triangle, and that matches up with, say, 12 on the larger. And I know the perimeter of the larger triangle, in this case, 84. What I don't know is the perimeter of the smaller. We can go ahead and let X be our perimeter and find it all in one go, instead of having to find each individual side. Notice it doesn't ask us to find the sides and then find the perimeter. It just wants the perimeter. So we can skip that step. So let's multiply this out. We'll take 84, multiply it by 5. And of course, we'll take 12 and multiply it by X. And then what we're going to do here, ultimately, this multiplication step, we really don't have to do it. It's sort of silly. So I'm going to go ahead, instead of multiplying 12 by X, I'm just going to go ahead and leave the 12 there. Again, there's no sense in doing that because ultimately we have to divide anyway. So if we multiply that out and divide, we should get a perimeter there for our smaller triangle of 35 units, whatever they're measuring in. So again, not only are the sides forming a proportion, but the perimeters form the same proportion with our sides. Right? So proving that doesn't take much. Obviously, if this segment is proportional to this segment, and of course all the others are as well, if I were to stretch the triangles out and make them one long piece instead of 3 that are shorter and connected, that same proportionality for, say, parts would then also have to be the same proportionality for the whole. Simple proof, not very formal, but it works. All right, let's try, if I can get my page to turn, some other parts. So not only are perimeters part of this whole similarity bit, but we can take a look at some others here as well. So let's take a look at these. The first one, if two triangles are similar, then the measures of their corresponding altitudes are proportional to the measures of their corresponding sides. So this is the one we kind of looked at there at the very beginning of our work. Notice if we've got similar triangles here, so let's mark them. So P and T, for example, Q and U, those of course are the same, and then R and V. Well, take a look. Here are the altitudes, QA and UW. Notice PAQ and TWU have to be similar. P and T are the same, the right angles are the same, and by angle similarity, we just need those two and we're set. So if QA forms a proportion with PQ as well as UW with UT, well, that means they're forming a proportion with these parts that are part of the overall triangle. So that's, again, a quick proof to show, yeah, it has to work. So again, altitudes will form the same proportion. And notice these are theorems, heads up. So special segments of similar triangles, theorems, they really don't have an individual name. From there, we can also show So let's see, we've got altitudes. We can also show that if two triangles are similar, all right, so the same triangles here, then the measures of the corresponding angle bisectors. So take a look. These are angle bisectors. They are not necessarily hitting those opposite sides at the midpoints. Okay, we got to get that clear. All this is doing is separating Q and U into two equal pieces, those angles. All right. So these angle bisectors, okay, the distance there is also in proportion. And again, we can prove this really quickly. For example, P and T are congruent based on what it means to be a similar triangle, because we know these two are similar. So I've got angle, angle, and then angle, angle again. Again, QB and UX form a proportion with QP and UT. And again, since they do that, that means they'll also form a proportion with the other sides as well. So these two are proved basically the same way, but altitudes and angle bisectors ultimately form the same proportion as the sides do. And again, very simple and easy to prove. My favorite, and again, I don't know why these are my favorite, but I like medians. They are fun. Medians do the same thing. Take a look. In this case, our median QM does not bisect Q. It does not form a perpendicular. All medians do that we know for certain is find the midpoint there of that opposite side, the midpoint there of that opposite side. That's all they do. Could they potentially be at a right angle? They could. Could they, in theory, cut that in half in a certain case? Sure. But all we know for 100% certain is that it hits that other side at the midpoint. That is all. All right. So we got to keep that in mind. So that median length, QM and UY, are also going to help us in this proportionality work. So take a look. I know that PQ, so this here, is going to be in proportion with UT. And PR and TV form that same proportion. So if we cut them in half, these smaller pieces will still have that same proportionality. And since P and T are congruent, we've got it by angle, side, angle, angle, side, angle. So QPM and UTY are similar. That means QM and YU form that same proportion as, say, QP and UT with the overall. So again, similar ways of doing this. All three of these are proved basically by us putting, let me grab the other one there. Oh, I can't grab it. There we go. So all three of these, whether we're talking about altitudes, angle bisectors, or medians, all of them are proven pretty simply by forming smaller, similar triangles within and using that information to show, hey, since this part is forming a proportion with the part that's part of the larger triangle, then it's all proportional together. All right, pretty simple, pretty straightforward. All right, let us talk about one that is different. All right, so put a star, highlight, underline something, the angle bisector theorem. This one is different, all right? Very, very different. Please, please, please keep this in mind. It's so different, it's not even funny. The angle bisector theorem involves one triangle, all right? Notice, for example, these others involve two triangles that we worked with, or two triangles that we worked with. This involves one, just one. Keep that in mind. So let's read it. The angle bisector theorem. An angle bisector in one triangle separates the opposite side into segments that have the same ratio as the other two. In other words, it forms that same proportional relation. So let's take a look at it. We'll color code it to make it easier to see. I know that AD, so this segment here, matches up with AC, this side here. Okay. Similarly, no pun intended, DB, all right, this segment here, matches up with BC, this side here. So notice the relationship we have. The proportionality is between these parts of this side compared to the, so notice AD matches up with AC. Okay, they're the similar parts, so to speak. BD and BC form that other. Why does this work? All right, well, notice we can't per se use the same tact that we used here, where we simply separated it out and used similar triangles. Here's what I want you to do at some point today, hopefully before class. If not in class, we'll discuss it. How do we prove the angle bisector theorem? All right, and we'll touch on it a little bit in class, but this one proves differently than the others. The others, it's simple. We just break the triangles up into smaller, similar triangles. This one, we only have one triangle to work with. So how are we going to do it? So again, do some research, see what you can find. But again, this is how it separates it out. Notice we're not comparing two separate triangles. We're comparing the parts within one triangle to themselves for that proportionality. All right, let's do some example problems. If I can get my page to turn. Here we go. So this first example, we're going to look at perimeters. So in this case, I'm going to try and find the perimeter of triangle BCD. So BCD, this one right here. And we know that it is similar to FDE, so this triangle here. So we're going to do the same trick that we did earlier. We're going to use, say, this 8 and 12. So 8 matches with 12. And then what we'll do is we'll compare their perimeters. So for example, for the 8 triangle here, this one here, we've got 12 and 5, so that's 17. And then we'll compare the perimeter here. Well, we don't have the perimeter. We're missing those side lengths, so we'll call it x. All right. Well, let's do a little bit quick multiplication here. And again, I'm not going to multiply 8 by x. That's silly. There's really no point in doing that. Ultimately, we're going to have to take it and divide again when we're done anyway. So I'm just going to skip that step. So we're going to take, we're going to take 17 times 12. And we'll get 204 over 8. And again, I'm not going to multiply the 8 by the x because ultimately we got to divide anyway. We'll divide that by 8 and we get 25 and a half. 25 and a half. And again, if we wanted to, we could go back and find each of those sides and double check ourselves, but 25 and a half looks like a good answer to me. So, excellent. On we go. This one's fun. We're going to try and find the perimeter of FB, or excuse me, not the perimeter of FB. We're going to find the distance of FB, excuse me. If SA and FB are altitudes, and of course our two triangles are similar. So notice x and 5 match up. So x and 5, they match up. This 2 goes with x. We'll put it across. And then this 7 subtract x goes with 5. All right, let's start multiplying. 5 times 2 is 10. 7 times x is 7x. X times x is x squared. So in this case, a negative x squared. We've got quadratics. So if you remember your quadratic work and how we're going to solve this, it's a lot easier if we can make this positive. So I'm going to shift everything to the right. So I'm going to subtract by 7x, add x squared. So we end up with 0 equals x squared, subtract 7x, add 10. Right? So solving these, remember we have a couple of options. One option is to use the quadratic formula, which is really long and drawn out. I don't really want to do that if I can avoid it. The other option is to factor it out. In other words, we're going to do FOIL in reverse order. We use FOIL to multiply polynomials. So when we factor, we're kind of doing FOIL in reverse. We're trying to see what those two numbers would be. Two polynomials, that is. So let's try that first. And if we can't make this work, then we'll use the quadratic formula. So in these first terms, because remember FOIL is first, outer, inner, and last. In the first terms, right, we need to figure out how to get x squared. Well, to get x squared is simple. By multiplication, it's just x times x. So that was easy. All right, let's try the last terms. To get a 10, we only have two options. We can either multiply 1 by 10, or we can multiply 2 by 5 in either order. Since we're trying to get a 7 in the middle with our outer and inner terms, I think 2 and 5 would make more sense. Now notice this is negative where this is positive. So what we're probably going to need to have is a negative 2 and a negative 5, because negative 2x and a negative 5x, again, those inner and outer terms, would get a 7x once we add them, and negative 2 times negative 5 is a positive 10. So that looks like a good factorization. Now remember, both of these multiplied together equal 0. So that means at least one of them is equal to 0, or potentially both. So we're going to solve both of these as if they were equal to 0 to see what our potential solutions could be. So x subtract 2 could equal 0, or x subtract 5 could also equal 0. So if we solve that, x could be 2, or x could be 5. So those are our potential answers, but let's try it. If I plug 2 in, while mathematically it seems to work, it doesn't work geometrically. Take a look. If x is 2, well, there's no way that works. S to A is the shortest distance possible. And notice, since this is not the same line, there's no way that that can be 2. So while mathematically it might work out, in the real world, not so much. So x is equal to 5 is going to be our best option. So if I take that and plug it back in, 5 subtract 7 is 2. And then, of course, if x is 5, that means this is 5 as well. In other words, these two triangles are exactly the same size. So clearly not drawn to scale. But if we're wanting to know what FB is, in this case, it's going to have to be 2 units, whatever they are. We don't care. All right, next two problems. And this will be our last. Yes, they'll be our last. So once again, we've got similar triangles here, and I know they are similar. Notice we've got our angle here matching up with that one, and our angle here matching up. And notice this is a median in both cases. We don't really need the medians, but they are what they are. So let's set up our proportion. I know 12 and 32 go together, so 32 and 12. I also know that the 2x subtract 3 goes with the 32, and then the x subtract 5 goes with the 12. So we got like items across from each other or top to bottom. Let's start multiplying. So 32 times x is 32x. 32 times 5, I'm drawing a blank. 160. There we go. 12 and 2 is 24. 12 and 3 is 36. Excellent. So let's go ahead and subtract here. So we'll subtract 24 and 32. So that is 8x. And then while we're here, let's go ahead and add the 160 to the negative 36. And that's 124. Next, we divide by 8. And we get an answer of 15 and a half. Cool. So 15 and a half is what x is worth. And notice they didn't ask us what the sides are. So we'll just leave it at that. Last problem. Notice in this case, this is a problem that works like our angle bisector. So again, these are the proportions that we'll need to set up. So let's color code it. So this segment here goes with this side here. They're like items, so to speak. And then move that out of the way. And then we've got our x over here and this side 14. They're like items. So again, I like to color code them. Just makes it easier to see for you guys. As you do your work, hopefully you'll start learning those relationships and won't need to color code. Let's figure out this distance real quick. The whole distance is 20. This distance is x, so we're going to subtract them to find this distance. So this side is 20, subtract x, and we'll go from there. So let's go ahead and set them up. So 20 subtract x is a like item, so to speak, with 11. And then across from that, we'll put x, and its like item is 14. All right, well, let's start multiplying. 11 times x is 11x. 14 times 20 is 280. And then negative x times 14 is a negative 14x. All right, let's go ahead and add 14x to both sides. So 280 is equal to, what is that, 25x. And then we'll take our 280 and divide it by 25, and that gives us 11 and 2/10 for x. And again, that's all we were asked to find, so that's all we'll write down. So today, we'll be looking at our special segments here, seeing how they're similar. Remember, before class, if possible, see if you can find a way to prove the angle bisector theorem, because its proof works differently than any of our others. All right, we'll see you in class. Have a good day.